Welcome to this explainer. Today, we're diving into one of the absolute most fascinating pivots in the entire history of physics. I want you to picture something for a second. Imagine a sealed glass box, and inside that box, there are trillions upon trillions of invisible molecules, just relentlessly bouncing off the walls and smashing into each other at unimaginable speeds. Now, if you were tasked with tracking the exact path, the speed and the location of every single one of those bouncing molecules, how would you even begin? I mean, it sounds like an absolute nightmare, right? Well, it's incredibly fascinating to see how physicists conquered this exact mind-bending problem. And in doing so, they completely accidentally laid the groundwork for quantum physics.
So here's our roadmap for today. We'll start by looking at the problem of thermal motion, see how averages basically saved the day, and unpack something called the equipartition theorem. After that, we'll test it out against different molecules, visualize it with Maxwell's distribution, and finally, we'll see how this whole thing set the stage for quantum theory. Let's get to it.
All right, Section 1, the problem of thermal motion.
Okay, so the kinetic theory of heat established a seemingly simple but really profound concept. Heat is, at its very core, simply the result of the random motion of the numerous individual molecules that make up all material bodies. But here's where we hit a massive wall. If heat is just molecular motion, to truly understand the thermal properties of a body, you might think you need to map out every single molecule's journey. But our sources are incredibly explicit about this. Trying to follow the motion of each single individual molecule participating in that thermal motion is not just mathematically impossible, it is entirely purposeless. The sheer scale of it is just way too immense.
Which brings us nicely to Section 2, the power of averages.
So how exactly did physicists like Ludwig Boltzmann, Josiah Willard Gibbs, and James Clerk Maxwell solve this tracking nightmare? Well, they radically shifted their perspective, and there's a brilliant analogy from our source to explain this. Think about a government economist for a second. When they're studying the national economy, that economist doesn't bother to know exactly how many acres are seeded by one specific farmer, let's call him John Doe, or exactly how many pigs he has on his farm. It just doesn't matter at that macroscopic scale. In the exact same way, a physicist does not care about the precise position or velocity of one particular molecule in a gas. All that counts, what is actually important for the observed macroscopic behavior of that gas, are the averages taken over a massively large number of those molecules.
Moving right along to Section 3, the equipartition theorem. Now that we're talking about averages, we need some ground rules. Statistical mechanics is essentially the study of average values for massive assemblies of particles in random motion. And one of its most basic laws, which is actually derived mathematically straight from Newtonian mechanics, is the equipartition theorem. It clearly states that the total energy contained in an assembly of a large number of particles that are constantly exchanging energy by crashing into each other, is shared equally, on the average, by all the particles.
Our source states this perfectly. If all particles are identical, all particles will have, on the average, equal velocities and equal kinetic energies. Think of a pure gas, right? Like pure oxygen or neon. Because all the particles are exactly the same, the math is just beautiful in its simplicity. If we use the letter E to represent the total energy available in the system and N for the total number of particles, we can find the average energy per particle simply by dividing E by N. Super straightforward.
But wait, Section 4, heavy versus light molecules. What happens to these nice, neat averages when things aren't quite so uniform?
Let's look at what happens when we mix different kinds of particles together, like a mixture of two or more different gases. The absolutely crucial point here is that kinetic energy is proportional to the mass and the square of the velocity. Because the energy must remain shared equally on average, the more massive molecules have to compensate by having lower velocities. Let's use a mixture of hydrogen and oxygen as an example. An oxygen molecule is 16 times more massive than a hydrogen molecule. So to maintain that equal average kinetic energy, the oxygen molecule will have an average velocity that is the square root of 16, which is 4 times smaller than the hydrogen molecule. Basically, the heavy molecules sluggishly drift around while the light ones zip around rapidly, but their average kinetic energies match up perfectly.
All right, Section 5, visualizing Maxwell's distribution. So, in a massive assembly of particles, individual velocities and energies are constantly going to deviate from the average. We call these deviations statistical fluctuations. Now, fortunately for us, these fluctuations can also be treated mathematically. But how can we possibly visualize this kind of statistical chaos? How do we picture the relative number of particles that are going faster or slower than the average at any given temperature?
Well, J. Clerk Maxwell completely mathematically solved this, mapping out these beautiful curves that, appropriately, carry his name. If you look at this chart, notice how the number of molecules plots against their velocities for 3 different temperatures: 100 degrees Kelvin, 400 degrees Kelvin, and 1600 degrees Kelvin. Take a really close look at how the shape of that population changes as the heat cranks up.
Breaking this down, the first thing to notice is that since the total number of molecules in the continuum doesn't change, the total area under all 3 of these curves remains exactly the same. But as the temperature goes up, the curve flattens out and the peak physically shifts to the right. This shows us that the average velocities of the molecules are increasing proportionally to the square root of the absolute temperature. And the wider the curve gets, the wider those statistical fluctuations are around the average. It's really fascinating, actually. Our sources note that this statistical method was incredibly successful in explaining the thermal properties of gases. Why gases specifically? Because the math is hugely simplified by the fact that gaseous molecules fly freely through space rather than being packed tightly together like they are in liquids or solids.
Which leads us to our final stop today, Section 6, Setting the Quantum Stage.
We've spent all this time understanding the chaotic, statistical nature of heat and gases. But you might be wondering, what does this have to do with quantum physics? Well, it turns out this entire framework was the absolute mandatory stepping stone. The roots of Max Planck's revolutionary discovery, the realization that light can be emitted and absorbed only in the form of certain discrete energy packages, or quanta, goes directly back to these earlier studies by Boltzmann, Maxwell, and Gibbs. Without this statistical description of the thermal properties of material bodies, without understanding that you literally have to zoom out and look at the mathematical averages of chaotic motion, Planck could never have formulated his groundbreaking theories on light quanta.
By finally accepting that they couldn't track every individual molecule, physicists didn't just solve the mechanics of heat. They quite literally accidentally unlocked the quantum nature of the universe. It really makes you wonder, if mastering the chaotic motion of random molecules unlocked the quantum secrets of light, what other completely impossible chaos is currently hiding the universe's next great discovery? What other problems out there just require us to stop looking at the individual pigs and start looking at the whole farm? Keep that perspective in mind the next time you're faced with an overwhelmingly complex system. Thanks for joining me on this explainer, and I'll catch you next time.